doing homework 5 part C. So you can see that this is the reactor that we had in part B. So we have our trickle bed reactor, our distillation chamber, and then our heterotropic distillation. So in this we have, in parts B, we thought of this as just an alkene of water and coming into the system, and then an ether and alcohol leaving the system. And we did a material balance for that. But we're going to do a material balance for each part of our reactor. We're going to do our material balance for a reactor, our distillation chamber, and then our heteroazeotropic distillation chamber, right? So let's look at this real quick. So we can see that we have, okay, so when we're looking at this, we can see that we have our, okay, so when we're looking at this, we see that we have an alkene of water coming in and then water coming into our trickle bed reactor. And then we have some flow leaving that reactor going into our distillation chamber. So let's draw this. So this is our reactor chamber here, right? And so what is coming into this system, right? What is coming in is we have our alkene flow. This is, we're gonna denote this reactor as our R, right? And then we're gonna highlight what's coming in, and that's an alkene, and that's a water. And then we have the alkene and the water coming in, and that's reacting. And then what are we getting? What's leaving the reactor is gonna be our feed to our distillation chamber, right? So that feed, we're gonna denote this as DIF for the feed for the distillation chamber. Okay, so then the next one that we want to do is, let's go over here, and this is our distillation chamber. So we're going to denote this as a D1. And then we're going to come over here and we're going to highlight what's in our azeotropic distillation, and we're going to denote this as AZ. So we have 3 parts of this system. We have the reactor, the distillation, and the azeotropic, right? So let's look at what's going into and out of these systems. So let's go down here and look. We first have what's going out of the distillation. We have the backflow of this water. So we're going to call this D1B. And this is the water recycle that's coming out of the distillation chamber. This is D1B for D1 backflow. And then let's look at this. So then we have some coming out of the top of this, right? So this is going to be our distillate. This is our distillate for our heterotropic distillation, right? So we're going to denote this as D1D for our distillate, right? So now let's come over here and look at this heterotropic distillation. So we have coming out of this system, we have a ether and we have an alcohol, right? Our ether and our alcohol like we had in part B. So these are coming out of the system. These are our products of the system, right? So the last thing that we have is our decanter water, and this is what's coming back into this recycle flow. So we're going to call this our decanter water. This is going to be coming from the azeotropic distillation. Okay, so let's look at some code of this. Let's look at this. So this is going to be, let's pull up our code. So this is going to be our code from part B, so we're just going to add on to this, right? So let's look down at this part C here. So if we look at our imports from the GitHub site, we see that there is something called, we have our JAX function, and all of this is from our part B. So if we go over here and we look, there's a function called .dict. So what is that? That is going to be a library where we're going to hold information at, right? So instead of having just like arrays that we're going to like call back on, This one is just going to have, it's going to store all this information in this dictionary. So let's use this dictionary, right? So it's just gonna hold all of this information. It's gonna be very condensed, very efficient, especially if you're gonna use it to find multiple variables. And we're gonna have a very big system, and we're gonna have to find a lot of variables. So if you're doing over than 4, you should really be using a dictionary. So let's do E equals dot dict, and then just some parentheses, okay? And so in front of each variable that we have, like the stoichiometry, we're just gonna put the .e in all of this. So this is gonna do, when you do this, it's gonna save all of these functions that we have into this library. Okay, so, and then the alkene comp, and then the ether comp. So all of this stuff is going to be put into this dictionary. Okay, no. Okay, so after putting all of these on here, so we're doing the ether flow, the alcohol flow, and okay, so after we do this, we're gonna do so these are our guesses for ether and alcohol, right? So let's do our extent of reaction 1 and our extent of reaction 2 as well. So after this, let's look at our function here. So what is another thing that we can do to this? So now let's look at our equation. So let's just pull up E dot alkene. So our E dot alkene, and let's do the composition, and let's just see what it pulled from our library. Look, so it pulled the array of 1.100, right? So this is gonna hold all our functions in here, and it's gonna hold it as an array. So it can call back this array on any kind of variable that we have. This is gonna be able to store a lot of data on here without having to call back individual items, right? So let's also look at, so we're looking at right now, we're gonna look at the equation. So we have a range function, and our range function is going to be a guess. So the first one is the guess of what it is. So our ether flow, let's say it's 5. And then we're gonna put 0 as our minimum. And then our last one is going to be our maximum this can be. So if we think about the ether, we think it's gonna be a reaction 2. So in ether, it takes 2 isopropanols to make 1 ether, right? So it also takes 1 isopropanol, takes 1 propylene to make 1 isopropanol, right? So that means we're going to divide the ether flow by 2, since it's going to take 2 moles of this alkene flow, right? So let's type this in here. So we also know that since it takes 2 moles of this ether flow, it's going to take 1 mole of this isopropanol, which is our alcohol. Also with this range function, what it does, it's going to give you a range of kind of a guess it could be, right? So by putting this as 0, it's going to cut out all of these negatives, right? So we want all of our ranges to be in the positive zone, because what we're trying to do is a positive flow forward. So let's write E, and it's going to be the alkene, right? So alkene. And then this is just going to be the flow, not the composition. And then we're going to do divided by 2, because this is the largest it can be, right? It can't be the alkene flow. It can be twice as, it could be 2 less than the amount. So let's do the alcohol flow, and let's do the range of it. So the first one, again, is going to be just the guess that we had. So let's just do 100 again. And then it's going to be a 0, right? And so then we're going to have, if we think about our alcohol, it takes 1 propylene to make 1 alcohol, right? So since we're doing 1 propylene to make 1 alcohol, we're going to just divide. We're not going to divide by anything. It's just going to be the alkene flow is the highest it could be. Right? Okay. So next, let's think about our extent of reaction 1 and 2. So let's do our range function. Extent of reaction 2. Extent of reaction 1. So we're going to do a range function, right? Because this is a guess. And then what should it be? So the smallest that it could be is our alkene flow divided by 2. And then our 0 is going to be our minimum. And then our maximum, let's think about our maximum. So the extent of reaction 2, it's going to just be our alkene flow, right? Because that is what the flow of it is. The extent of reaction 2 is going to be the flow of the alkene, right? And the minimum it could be is half that alkene flow. So then let's look at extent of reaction 2. So let's do the range, and then since it takes 2 isopropanol to make 1 ether, the extent of reaction 2 should take twice the amount. So we're going to have to divide this by another 2. So we're going to divide it by 4 because we're going to add on to it. So like we had in part extent of reaction 1, we had divided by 2 as the minimum. It should be divided by 4 since we're using 2 moles of isopropanol to make 1 mole of this. So let's do the alkene flow, right? Divided by 4, and then we're going to have the minimum as 0. And then for our maximum it could be, it's going to be the same thing, just divided by 2. So it's going to be the alkene flow divided by 2 is the maximum it can ever be. Okay, so let's do shift enter. And then let's look at the equation, right? Our equation for a vector. So what are we going to do here? So we have a vector. So our vector holds all of our inputs that we need, any variables that we have. But let's think about this as if we have so many variables or so many unknowns that we have, doing this vector is going to be extremely hard because you have to figure out all of these. So instead of doing a vector, let's do a dictionary. And let's just denote it as D for dictionary, right? So let's take out this vector itself because we don't need this. And we're just going to focus on this as a dictionary. So what we're going to do is we're going to put D in front of everything, and this is going to be denoted as a dictionary. So when we're solving this, or when we're going to put this into our root function, we're going to put our dictionary into this, and our dictionary should pull all of these from the dictionary, right? So let's put D in front of all of these. So D, okay, and then let's go to our feed. So D here, D for our water comp, and then let's go to D for our alkene, D for our alkene comp here, and then our alkene, our ether flow, our ether comp, our alcohol, and then our alcohol comp, right? So this is all going to be having under a dictionary, right? So, okay, so that's all the information that we know now. So let's go back and let's figure more of this problem out that's not in the code, right? So we're going to look back at this reactor here, okay? So the first thing that we want to look at is this distillation chamber, right? So this distillation chamber is going to have our vapors and our liquids together, right? So let's pull up this frame right here. So our distillation chamber is going to have liquids and they're going to have vapors, right? So if we look at here, we're coming in with those, and we know that Raoult's law talks about liquid. And when we write down Raoult's law, let's write down our X of I, which is going to be our mole fraction of our liquid phase. And then we're going to write down our saturation pressure at some temperature I. And this could be at any temperature, so we're just going to note this as T, and then we're going to equal, and this is going to equal our mole fraction of our gas phase, which is Yi, and then we're just going to have our saturation, just our total pressure of P, right? So this is Raoult's law, and it's going to talk about the relationship between our mole fractions of our liquid and our mole fractions of our vapor. So let's go over here and kind of draw what's happening. So let's happening. Let's have this box, right? And inside this box, we're going to have our liquid and our vapor phase. So our liquid and our vapor. And then inside our liquid and our vapor phase, we're going to have mole fractions, right? So mole fractions of our component. And right here is our interface. So our interface is the phase, it's the equilibrium between our vapor and our liquid, right? So let's go and write our mole fractions. So there's going to be mole fractions of each component in here. So let's just denote them as our X of I, our Yi, Y2, and Y3. These are just going to be our mole components. And then X1, X2, and X3 in our liquid. So let's think about this. So we have all these mole components, right? And we have our mole fraction of our vapor phase, and we have the mole fraction of our liquid phase. So if we can go over to Raoult's law and kind of derive our Y of I, so our mole fraction of our vapor phase. So this is going to be our mole fraction of our vapor phase over the mole fraction of our liquid phase, and this is going to equal the pressure, saturation pressure of a pure component at some temperature, right? Divided by our total pressure. So let's look at this saturation pressure over our total pressure. This is going to be called our Ki constant. Okay, so for our Ki constant, let's write down our, we're going to have a distillation chamber we're going to have a phases between our our vapor and our liquid, right? And these are going to flow in between each other. So let's look over here for a second. So over here, we're given this mole fraction ratio of the components for this D1 chamber right here. And you can see that it's, so for our Ki, what we know is that we have our mole fraction ratios, and those are 100, 10, 5, and 0.2. And those mole fraction ratios between the vapor phase, the mole fraction of the vapor, and the mole fraction of our liquid, that is our Ki constant. So let's write this down first. So we have our dKi, because this is for a distillation chamber, for our dKi. And we have 100, we have 10, we have 5, and we have 2.2. So then we have this relationship between these KIs and the mole fraction of our XI and the mole fraction of our YI, right? So since we know that the first one is our vapor, we're going to do dk, the Ki constant, and this is going to equal, so we could look over here, and this is our vapor, right? But let's show this picture first. So we have in our distillation chamber, we have our vapor and our liquid stacked onto each other. All of these kind of phases between our liquid and our vapor and our liquid and our vapor. And these are going to interflow with each other. This is going to be a multi-phase flowing system in our distillation chamber. So all of these phases are going to be stacked on top of each other, our vapor and our liquid, and they're going to flow within each other. And so with this, we can kind of understand now how to write this equation. So our vapor. So our vapor of the distillation chamber is going to be the distillate, right? The distillate of our distillation chamber, that's going to be our vapor. So if we go back over here, we can kind of see that we have our backflow of water. That is going to be our liquid phase. And then we have our distillate, right? That's going to be our vapor phase. So if we do these and we multiply these by our mole fractions of them in the vapor or the liquid phase, we will be able to get kind of the dk constant at the distillation chamber. So let's kind of write this down. So it's going to be, so let's do our our distillate, so D1D. So D1D, our distillate, times YI, which is the mole fraction of the vapor phase, divided by the backflow of water from the distillation chamber, right? And times the mole fraction of our liquid. Right? So this is going to be our Ki constant. So, and these, so if we subtract them together, we're going to be equal to 0. So this is one way that we could check ourselves, is to see if this equals each other, and which would help find our Y of i's and our X of i's in these distillates, right? So the next thing that we kind of want to talk about, and then we're going to kind of talk about, is like these mole fractions, because these have these mole fractions in them, right? And if we think about this Ki constant, for each of them, so for each of our our Ki's, we're going to have our list out right here. So our list is going to be our propylene, our ether, our alcohol, and our water, right? So this is going to be in the same list. And so then when we equal this to this like Ki, this like equation we made, that is going to have us it's going to give us 4 separate equations, right? So we're going to have one for our propylene, which is number 1 because that's the most volatile. And then we have our ether, our alcohol, and we have our water. So they're going to equal each other. And this is going to give us 4 equations, right? Because for each of them, we're going to have to equal it to it. It's a mole fraction. So this has some mole fractions to it. So let's just write down kind of like a flow with some mole fractions to it. And this is just going to be like a general guesstimate of like what is happening, right? So these are not exact numbers that we're going to be using. So let's just say we have some flow of 100 moles per second. And we're going to have a mole fraction of Z1, which could be like 70. And then we're going to have a mole fraction of Z2, which could be like 10. And then we could have a mole fraction of 3, and these can equal 15. And we have a mole fraction of 4, which could just equal 5. So these don't have to be exact. They're just kind of we're just guessing. There's not a rhyme to it, but we're just going to do this. So now if we do our mole fractions divided by our flow rate, we're going to get a fraction of 7 over 10, and then we're going to get 1 over 10, right? And then we're going to get 15 over 100, and then 5 over 100, right? So if we add all these up together, you're going to notice something, that these are going to equal 1. So we can kind of understand that there's a constraint to this, right? That if all of these equal 1, then the constraint of our system is that all our mole fractions have to equal 1, right? All of our mole fractions added up together have to equal 1. So let's write this down. So Z12, Z13, C14, all have to equal 1. So this is a really big constraint, right? Because they have to be a fraction and they have to equal 1. So we're looking at the system from 0 to 1 because it has to be 1. Like it has to be in between 0 and 1. This can't be, none of them can be 0 and none of them can be 1 for our mole fractions. So this is very limiting, because we're not going to have a wide range of what we're able. So we're not going to have a wide range of what we're able to see. So let's try to do something called a variable transformation. And this is going to help with trying to have something that is less limiting. So we're going to do x of I equals, and we're going to do e to the vi divided by 1 plus the summation of e to the vi, right? And so this is going to be from I greater than n. So the next thing that we want to do is we're going to have an x of n, and our x of n is going to be 1 minus the summation of our x of i's. And this is going to be for when I equals n. Okay, so let's think about this real quick. So we're going to have, let's say that our v of I is a really big negative number, right? Because our v of I is going to be a very big negative number. And when you do e to a very big negative number, you're never going to hit 0. You're just going to get increasingly smaller and increasingly close to 0. So let's say we have negative 1,000, right? And we make this into like e. E is going to get really close to 0. The graph of E never hits 0. It becomes kind of closer to 0, right? So if we think about that, the top of our fraction will never equal 0. And then let's look at this bottom here. So we have 1 plus the summation of all of these really, really, really tiny numbers. So our x of I is never going to equal 0. And then we have 1 plus whatever. So that means we're never going to be dividing by 0. So this is correct. So it's just check case here. So since we're adding up all of these tiny like fractions here, we're going to have our x of i's, right? And then let's look at our x of n. So our x of n is going to be our last component mole fraction, and it's going to be 1 minus all of these tiny numbers that we have together minus 1. So what this means is all of these things added up together will equal 1, which is one of our rules that we need to know. So they're all going to equal 1 here. And so if we're doing really, really tiny numbers minus that, we're given the freedom of our first 3 components. So let's say we have a 4-component system. The first 3 components are going to be in the xi's. Okay, so let's look at this x of n again. So our x of n is going to be our last component, right? And so our last component is the only one that's going to be restricted in this case, because we're going to have x of i's, the first 3 components, being able to, they're able to have this like limitless range, while our x of n is just going to be subtracted by all of these together. So let's write this down. So let's write down the rules that we need for this. So the summation, so all of them added up for our mole fractions have to equal 1. And then our second rule for this is our mole fractions have to be between 0 and 1. So if we look at this, our x of n are 1 minus all of these summations of our x of i's are going to equal 1, right? So when we're doing 1 minus our x of i's, it's going to be all of our fractions are going to equal 1. And then 0 to x to 1, right? It's never going to be bigger than 1 since we're going to subtract by 1. And it's never going to be 0 because we have this 1. It's going to get closer and closer to 0, but it's never going to be 0 because of these e functions that we have, right? So this checks out as well, because if we have a negative number, it's never going to be negative in our mole fraction, but we can look for a negative number because of that. So this is true, right? So this is able to go by these rules of our function. So we're going to be able to do a negative infinity to infinity interval. Okay, so it checks off both of them, right? So this is going to have a limitless show, right? So this is going to be from a negative infinity to infinity, which is so much better than our original mole fraction because that was so limiting. Now we can look from our first 3 components. We can look from a very interval from a negative infinity to infinity. While this one over here, we would have to look from a very small interval. So this is this is why we're going to do this variable transfer, right? So this variable transfer helps us be able to look at the system in a bigger interval, right? Let's look at our equation. So we have our updated Python with our dictionary. Let's define another equation. So let's just say equation 2, and this is going to have, we're going to pull in a dictionary for this, like we did in the earlier part. So let's look at a reactor. So we're going to do a material balance for a reactor, right? So let's do our feed. So this is going to be the same thing as our feed for the first equation, but we have to account for our water, right? So let's just put that in there. So now we have to account for our water, right? So our water that's going to be recycled. So that is going to be our decanter water and our backflow water from our distillation. So let's just add this. So let's go add, and then let's do our D dot, and then D1B, so our backflow of water from our first one. And then we're going to multiply this by our composition, right? So this is going to be the backflow and then times our composition. And then let's add our decanter. So D dot decanter. So right here you can see that this is the decanter and the flow go back to this recycle here, which go back to our reactor. So this is feeding our reactor. So decanter times our decanter composition. Okay, and then the next thing that we want to do is going to do our reaction. So, and our reaction is going to be the same because we did the stoichiometry for it, and we did what's coming in and what's leaving the system. So let's just say react, and then let's just copy what we have in our equation 1, right? So, and then we're going to have our reactor product, because this is what we are going to want to do, what is produced by this. So reactor product and this is going to equal our D1 feed, right? Because that's what's being produced from our first reactor. So the D1 feed and then times our D1 feed composition, right? So this is the only thing that's actually leaving our system for our first equation, for our first reactor. So the next thing that we want to do is our reactor balance, right? So let's write reactor balance. And this reactor balance is going to be pretty much the same as our first equation, where we're going to have our feed plus our reaction minus our product. So let's do our reactor feed minus our reactor, plus our reaction, and then minus our reaction product, right? Because our product is leaving the system, so we have to subtract that. Okay, so this is the end for the reactor balance. So let's try to do our, that's right. So the first thing we're going to do is, so let's say D1 and then let's say balance, because we're going to want to do a D1 equation for this. And let's say we're going to have our flow coming in, which is going to be our feed, right? Our feed to the system, and then we're going to subtract this by, and then we're going to put this in parentheses and just add whatever we're going to subtract. So what is leaving this? Well, we can see that it has the backflow of water and has its distillate, right? So let's put our distillate times our distillate composition, right? Because this is leaving the system and it's going to go to the azeotropic distillation, and then we're going to add this. We're just going to, let's copy this and then just paste it over. So we're going to change this to our backflow of water for each of them. Azeotropic balance, right? So let's think about this. So we have our balance of our azeotropic and rebalance of our DI, right? So our balance of our azeotropic, what's going into our azeotropic? We have our distillate, right? So let's copy our distillate because this is going to be feeding our azeotropic distillation, right? So let's do this. And we're going to subtract this by what's leaving our system. So we have our decanter water, and we have our ether and our alcohol, right? Our products are going to be our ether alcohol, so they're going to leave. And then we have our recycled decanter water. So let's just copy this decanter water here for our composition. So decanter water, and then we're going to add this too. And let's add this ether and alcohol as well. Leaving our system is our decanter water, our ether, and our alcohol. So the next thing that we want to do is we are going to look at our here. So when we see down here, we're going to look at this, our Ki constant, right? So our Ki constant is going to be 100, 10, 5, and 0.2. So let's do our dKi, right? we're going to do dk, we're going to do d1, and then we're going to do our vapor, our liquid, and at equilibrium, right? So this is pretty much what our Raoult's law is. So we're going to do, if we subtract this array of our Ki constant minus our composition of it. So let's do our mole fraction. So di1, our distillate, and we're going to divide this by our D, our backflow of the water, and we're going to subtract this by e to the dki. Oh, and this has to be the composition of it, right? Because this is going to be the mole fraction. So the mole fractions are given to us as the composition. So these have to be the composition. So let's go back up here. And we are going to see that, let's just write down e to our Keg-I constant, right? And that is given to us as our mole fraction ratio. So it's going to be 100, 10, 5, and 0.2. So let's just do d dot dk, and we have our D2N2, which is going to be dictionary named tuple, right? So let's, so our D2N2 is going to give us, so our D2N2 is dictionary name tuple. And our dictionary name tuple is going to give us a lot of values of like our initial, our unknown. It's going to wrap our functions. So let's just write down, so it's going to be our initial, so XO, and then it's going to be our wrap of our X2 unknown, and then it's going to give us our dictionary name tuple, and we're going to put it in our dictionary that we made, which was E, right? So let's write this down, and we're going to use these to help us solve for our initial values, help us wrap and find the unknowns of this, right? So our D2N2, and this is going to be from E. Shift enter, shift enter, shift enter. Okay. So let's look at this as our unknown function. Look at this as our unknown function, our X2 unknown. And we're going to put in our X initial. And this is going